Okay. So we said that if you have a line on a surface, then it's already a geodesic. Remember that geodesics are length minimizing curves. So if you have a line on a surface, surely it is the length minimizing curve. Okay, but we didn't prove that geodesics are length minimizing. We didn't prove that, but that's a fact. Okay. Now let's see some examples. Let P, or let's say gamma, be a plane in R3. If alpha is any curve on gamma, then of course alpha prime dot product u is 0, u being the normal vector of the plane. Let's say u is this normal vector of the plane, and we have any curve alpha here. If you take derivative, hence taking derivative, of both sides, we see that derivative of 0 is 0, but derivative of this is what? 0 is equal to derivative of the first term dot u plus derivative of this times derivative of u prime. But u is constant along the plane, right? The normal vector of the plane doesn't move. So this is 0. Well, meaning that alpha double prime with u is dot product with u is 0, meaning that acceleration vector is always normal to the surface. Hence, alpha is a geodesic. Okay. Geodesic if alpha prime is no. Bir dakika. Yok. Şöyle demem lazım. Geodezik olduğunu buradan doğrudan görmüyoruz da şöyle yazmam lazım. Now, if alpha is a geodesic, Then second derivative of alpha is lambda times u for some function lambda t, right? Because geodesic means its acceleration vector is perpendicular to the surface. Okay. Now let's put this into this equation. Then if alpha is a geodesic, we have uh, 0 is equal to alpha double prime dot u, but alpha double prime is just lambda times u dot product u. So this is just lambda times u dot u. U is a unit normal vector, so this product is just 1. Therefore, we get lambda, meaning that lambda must be 0 as a function. Hence, thus alpha double prime, which is just lambda times u, must be 0 times u, which is 0. Okay. Pardon. Buradan onu görmüyoruz. Yani buradan gördüğümüz şey alpha double prime 0. Tamam. Alpha double prime is 0. Therefore, alpha prime t is just a constant vector q, a constant. Hence, alpha t is what? If you integrate this one more time, you will get p plus t times q for some p. So if it's a geodesic, then it has to be a line. So that alpha is a line. And we know that if you have a line, then it's already a geodesic. So we see that if you have a plane, the only geodesics on that plane are the lines. As a conclusion, we see that on a plane gamma in R3, a curve alpha is a geodesic if and only if it's a line. Okay. Tamam mı? Reasoning şöyle. On a plane, we always have this. And then we take derivative and we see that on a plane for any curve, this inner product is 0. Now, if this is a geodesic, then by definition, the acceleration vector is a multiple of the acceleration vector. Sorry, normal vector of the surface. So alpha double prime has to be like this. If you just take this and plug into this equation, then you see that lambda is 0, meaning that alpha double prime, which is lambda times u, is 0. Well, if second derivative is 0, then the first derivative is a constant vector, and therefore the alpha function is just t times that constant vector plus another constant. Therefore, it's a line. And we already know that if alpha is a line, then it's already a geodesic. So on a plane, the only geodesics are the lines, and every line is a geodesic. Tamam mı? In general, determining geodesics on a surface is a difficult problem. You have to solve a nonlinear ordinary differential equation. But on special surfaces like planes and spheres, they are kind of easy, okay? On plane, we already seen that geodesic is the same thing as a line. And on a sphere, we will see that we partly seen that geodesics are great circles, but we didn't fully prove that fact, okay? All right. Well, now let be a sphere and gamma, a plane through the center. Center of the sphere. Let alpha be a unit speed parameterization of the circle of intersection the circle of intersection what? Sigma and gamma. So you cut the plane, you cut the sphere by a plane through the center of the plane. Well, alpha is a circle. We have seen this. In this case, this is the acceleration vector of that great circle. The acceleration vector of a great circle is parallel to the normal vector of the sphere. Hence, alpha is a geodesic. Değil mi? Kürenin üzerinde bir circle, if you take a circle on a sphere, its acceleration vector is towards the center of that circle. But in that case, the center of the circle is the center of the sphere because it's a great circle. Therefore, the acceleration vector of the circle is parallel to the normal vector of the sphere. But this means exactly that, you know, alpha is a geodesic because geodesics are the curves so that their second derivative or acceleration vectors are perpendicular to the surface, right? Okay. Well, we already actually have seen this. As I said, we didn't prove the reverse direction. We will see later that they are the only geodesics of the sphere. Yani great circle'lar geodezik ve başka geodezikte yok. Okay. Well, let's see cylinders. So let's take a cylinder in R3 given by this equation. So it's a cylinder with base on the plane, right? The cylinder given by this equation. Okay, now claim is this: any geodesic on M has the form alpha t, which is just r times cosine at plus b, r times sine at plus b, plus ct plus d. So it's a helix, okay? This is an helix. If you think about it, so geodesics here are just helices, okay? All right, so they go like this. Şöyle çizmem lazım değil mi? İçini görüyoruz orada. Okay, now let's see why this is the case. Proof. Okay. Let alpha t, this is a curve on a cylinder. I can write it this way. You know, what's the surface patch for this? A surface patch for this xuv is what? It is just, so I have circle direction and horizontal direction. Circle direction is this: r times cosine u, r times sine u, and then the vertical direction is just v. So this is a parameterization for the circle. Sorry, for the cylinder. If you have a curve on a cylinder, right? This is the UV plane. That curve should be also given as a curve in the UV plane. So I have a curve in UV plane, and its image under the surface patch is a curve on the cylinder. Therefore, I can assume that any curve alpha on a cylinder, on the cylinder, has the following form. So this is just r times cosine gamma t, r times sine gamma t, and then ht, right? For some functions gamma t and ht. Right. So this is the general form of a curve on the cylinder, because this is the surface patch. The only variables are here, this u and v. So u and v are unknown functions, and this is my curve. Now let's see what should be the function gamma and h for alpha to be a geodesic on the cylinder. All right, so let's see that. By the way, what is the normal to this surface mu? Well, okay, let me choose maybe a different color. My normal vector u has the following form, right? X coordinate can be anything, y coordinate can be anything, but the z coordinate is 0, right? Because normal vector is always parallel to the xy plane. There is no z component of the normal vector. However, alpha is a geodesic. Since alpha is a geodesic, alpha double prime is parallel to u, right? It's normal to the surface, therefore it is parallel to the normal vector. And hence, so alpha double prime, what is alpha double prime? I am taking derivative with respect to t, right? So if I take derivative with respect to t twice, I will get again some sine and cosine terms here, again sine and cosine terms here, but here I'll just take derivative twice. So this component will be just second derivative of h. Therefore, okay. This is, you know, h double prime, and this is parallel to this vector u. Well, it means that h double prime must be 0. In particular, h double prime t must be 0 for all t, meaning that hence alpha ht is what? This is a real valued function of t. Its second derivative is 0. So the first derivative is a constant, and the function is just a linear gadget. So it is just ct plus d, right? So it has this form, ct plus d. All right. Now, we also know that, recall that any geodesic has constant speed, so that norm of alpha must be constant. But what is the norm of alpha prime? Well, I have to take the derivative of this. Let's see. Okay. is constant. Now let's see what is this. Alpha prime t. Okay, what is the derivative of this? This is just minus r ne yazdım oraya? Gamma mı yazmışım? Okay. Gamma prime t sine gamma t minus, no, not minus, r times gamma prime t cosine gamma prime t and h prime t. H prime is just, of course, c. So this is just c. Okay. So norm of alpha prime is then what? I have to take norm of this. Norm means you just square all these gadgets and add them up. You will get r squared gamma prime squared, r squared gamma prime squared, and then sine squared plus cosine squared, which is 1. So I have r squared times gamma prime squared plus c squared. So the result is just r squared gamma prime t squared plus c squared, and then square root of this. And this quantity is constant, right? So this quantity must be constant because this is the speed of the alpha curve, and alpha is a geodesic. Geodesic says a constant speeds. Therefore, this is constant. But if this is constant, well, this number is constant. This number is constant. Therefore, this has to be constant. Since it's constant, we see that alpha prime t squared is constant. Well, this is constant, means this square is constant. Hence, alpha prime t is constant. Well, this is constant, say a. So alpha prime t is equal to a. But this implies alpha t, gamma t is just at plus b for some b. So gamma is just at plus b, okay? Hence, alpha t is just r times sine at plus b, and then comma ct plus d. Okay. So we have determined geodesics on a cylinder. Of course, you know, on a cylinder, life is kind of easy because cylinder is basically the plane, right? I mean, you just take the plane and then just bend it like this. Okay, that's why life is easy on a cylinder. Although it looks like curved, actually it is flat. Okay, so cylinders are flat, spheres are not flat. Okay. Here is a proposition. Okay. Change the board. Proposition. As I said, in general, finding geodesics on a surface is not easy. But we know that, for example, through every point on a surface, there passes infinitely many geodesics. Actually, through every direction at a point, there passes a unique geodesic, okay? So there are many geodesics. In other words, you know, if you want to go in a certain direction, then there is a shortest path in that direction, okay? All right, now let gamma be a plane orthogonal to a surface at any point of intersection then the unit speed parameterization alpha t of the intersection M is a geodesic. So if you can find a plane which cuts your surface so that at every point of intersection, the plane is perpendicular to the plane surface, then the intersection curve is a geodesic, okay? For spheres, this is something we already know, right? If you cut the sphere by a plane which is perpendicular to the sphere, well, then that plane must be a plane which goes through the center of the sphere. Therefore, the intersection curve is a great circle. But this is true in general. And the proof is easy. The curve lies on the plane. Therefore, the normal direction of the plane, normal direction of the curve must be on the plane. But it's also, okay, let me just write down. Since alpha is a unit speed curve in P, alpha prime and alpha double prime are perpendicular to each other. Why is that? Because alpha prime dot alpha prime is 1, and if you take derivative, you will see that alpha prime dot alpha double prime is 0. Therefore, they are perpendicular to each other. Where both curves, now this is not P, this is gamma, where both curves lie in gamma. So here is my plane gamma, okay, and I have a curve alpha here. The tangent vector of this curve is here, and the normal vector is here. They both lie in gamma because, you know, the curve lies in gamma. Değil mi? Alfa gammada yaşadığı için alfa ile ilgili her şey de gammanın içinde, değil mi? Dışarısını bilmiyor zaten. Okay. Ama şunu da biliyoruz. However, U is in gamma. Why is that? Because my surface and the plane are perpendicular to each other. So the normal direction of the surface should lie inside gamma by assumption. So suppose this is my surface. Vazo gibi bir şey olsun şöyle. You cut this with a plane perpendicular to the surface. So if you cut it just like this, at the, biggest radius through the circle with biggest radius, then your plane will be perpendicular to the surface. Şuradan keserseniz öyle olmayacak. Surface normaliyle, if you cut it like this, the normal of the surface will not lie inside this plane. But if you cut it here, when the radius is maximal, then the surface will be normal to the plane will be normal to the surface. So this U also lies inside gamma. So where is that U? Okay, I don't know where U is. Somewhere here, let's say. But we know that alpha is a curve also on the surface. Therefore, derivative of alpha is also perpendicular to U. Since alpha is on M also, alpha prime is perpendicular to U. So this picture is not quite correct, okay? U and alpha prime must be perpendicular to each other. Well, this is possible only if U is parallel to alpha prime, right? This is possible only if alpha double prime is parallel to U. But alpha double prime is parallel to U means alpha is a geodesic. And alpha is a geodesic. This is a one-way theorem, right? It describes a family of geodesics. What are those? If you can find a plane which cut your surface at right angle at all points of intersection, then the intersection curve has to be a geodesic. Of course, once it is parameterized arc length with unit arc length. Yeah. If it is parameterized so that it has unit speed, then it's a geodesic. Okay. An example. Let M be a surface of revolution. Okay, so how it is obtained? Well, take any curve and just rotate this along an axis. Okay, so in this case, this axis. Şöyle bakayım çizebilecek miyim? Okay. What are the geodesics here? Well, I cannot tell you all the geodesics, but some of them are the following curves. Just take a plane containing this line and cut your surface with that plane. Okay, so with a plane containing this line, you just cut your surface. If you do that, you will get something like this, a meridian, right? A meridian. So this is the geodesic. And I told you another type of geodesic. This time you cut your plane with a horizontal plane, but you have to cut it at a point where the radius is either minimal or maximal. If you do that, again, your plane will be perpendicular to the surface, and you will get this curve. The maximal radius is this one, this curve, and then you have another one, a local minimum for the radius. These are also geodesics, okay? Geodesics. Because if you cut it like this, your plane will be perpendicular to the surface. Another example, maybe I have still a couple minutes. Ya da önce sileyim. Again, a surface of revolution. But this time you know better. Değil mi? Artık vazonun üzerindeki eğrilere eskisi gibi bakmayacaksınız, değil mi? Some of them are geodesic, some of them are not. Okay, another example. Take a Smith torus. What's a torus? This time you take a circle on the plane and again just rotate about an axis. You will get so-called Smith, right? Like this. What are the geodesics? You can cut, so this is the center of rotation. Take any plane containing this center of axis of rotation, and cut it with the plane. You will get circles. So all the meridians, okay, all the meridians, these are the meridians. These are all geodesics, okay. These are geodesics, meridians. No, they are not meridians, they are longitudes, right? Meridians, bunlar boylam. long, bunu doğru yazdım mı emin değilim ama. Meridians are the following. Not all meridians, right? Meridians with greatest or smallest radius, or well, it can be a local minimum also or maximum. So meridians with radius, a local extreme value of the radius. Okay, so what are those curves on the Smith? Two of them, the inner circle, right? The inner circle and the outer circle here, right? These are the two geodesics where the radius is minimal and maximal. So this is the minimal radius and this is the maximal radius. Okay, those two circles are also geodesics. But on a torus, there are a lot more geodesics. As I told you, through every point and every direction at that point, there passes a unique geodesic. So if you sit on a point like this, in every direction, there is a geodesic, okay? In every direction, there is a geodesic. And geodesics on the torus usually looks like this, okay? There are curves like this, goes, you know, they go like this. And usually they don't close up, okay? They continue like this infinitely many times. They fill the whole torus actually. So there are many geodesics, and we listed just few of them. Okay, let's stop now.